Somewhere between Mars and Jupiter, there is a debris field so vast that if you tried to walk across it, you would need a spacecraft, decades of fuel, and an enormous amount of patience. It contains, by the most recent estimates, somewhere between 1 and 2 million asteroids larger than a kilometer across, and many millions more smaller than that, down to boulders and pebbles drifting silently through the dark. Now imagine gathering every single one of them. Every asteroid in the main belt, every rogue rock crossing Earth's orbit, every Trojan asteroid trailing Jupiter, every fragment of shattered planetesimal left over from the birth of the solar system. All of it, at once, aimed directly at Earth. What would happen if every asteroid in the solar system hit our planet on the same day? It's a tempting image, because we've all seen the movie version of an asteroid apocalypse. A single mountain-sized rock screaming through the atmosphere, a fireball, a shockwave, that's the end of civilization in 90 minutes of runtime. But the real answer to what would happen if every asteroid hit at once is stranger, and in some ways more revealing than any Hollywood disaster reel. Because the truth is, most of the solar system's asteroids combined could hit Earth, and the planet would barely notice. And that single fact tells us something profound about scale, about how deceptive our intuitions are when it comes to space, and about why the very rare, very large impacts are the ones that actually matter. To understand why, we first need to appreciate just how much emptiness lives inside what we call the asteroid belt. Pop culture loves to depict it as a field so densely packed that starships have to dodge boulders tumbling past their windows every few seconds. The reality is almost the opposite. The main asteroid belt spread out in the gap between Mars and Jupiter is so sparse that NASA's Dawn spacecraft, and later the Lucy mission on its way to the Trojan asteroids, passed straight through it without so much as a near miss requiring evasive action. The average distance between two asteroids, larger than a kilometer in the main belt, is several 100,000 kilometers, further than the distance from the Earth to the Moon. If you were flying a spacecraft through the belt with your eyes closed, statistically, you would almost certainly come out the other side without hitting anything at all. And here's the piece that really reframes the whole scenario. Even if you could scoop up literally everything in the asteroid belt, every single rock, and press it into one object, the total mass would still be underwhelming. Current estimates place the total mass of the entire asteroid belt at somewhere between 3 and 4% of the mass of Earth's moon. Not 3 to 4% of Earth, 3 to 4% of the moon, which is itself a small fraction of Earth's own mass. Roughly a third to a half of that already tiny amount is locked up in a single object, the dwarf planet Ceres, which at about 940 kilometers across is really a small world in its own right rather than a typical asteroid in the way we usually picture them. The next three largest bodies, Vesta, Pallas, and Hygeia, sweep up most of the remaining mass. That means the millions of smaller asteroids we hear about in headlines, the city killers, the near-Earth objects that make the news every few months, collectively amount to a rounding error compared to these four giants. So let's actually run the numbers on the doomsday scenario. If you took the entire asteroid belt, all 3 to 4% of a moon's worth of rock and metal, and slammed it into Earth in a single instant, you would be delivering an object with roughly 1/25th to 1/30th the mass of our moon. That is a genuinely staggering amount of material, more than enough to obliterate every trace of life and fundamentally resculpt the planet's crust. In fact, delivering that much mass at asteroid belt velocities, which tend to be extremely high relative to Earth, would release energy so enormous that comparing it to nuclear weapons stops being a useful unit of measurement. We'd be talking about an event on the scale of the giant impacts that shaped the early solar system itself, the kind of collision that many scientists believe formed the moon in the first place, when a Mars-sized protoplanet nicknamed Theia is thought to have struck the young Earth roughly 4.5 billion years ago. Combining the entire asteroid belt into a single impactor would, quite plausibly, be an extinction-level, planet resurfacing catastrophe. But here's where the thought experiment gets interesting, because every asteroid in the solar system is a much bigger set than the main asteroid belt. It also includes near-Earth asteroids, the relatively small population. Currently more than 41,000 known objects and rising rapidly as new surveys come online, that orbit close enough to occasionally cross Earth's path. It includes the Trojan asteroids clustered in Jupiter's orbit, tens of thousands of them, likely more undiscovered than discovered. And if we're being generous with the word asteroid, it includes countless smaller bodies throughout the outer solar system as well. Yet even after we throw all of that in, we haven't meaningfully changed the outcome. Ceres alone so thoroughly dominates the asteroid population's total mass that adding every near-Earth object, every Trojan, every stray boulder in interplanetary space, changes the final tally by only a small percentage. The story of all the asteroids hitting Earth at once is really the story of what happens if Ceres, Vesta, Pallas, and Hygeia hit Earth, because everything else is essentially rounding noise stacked on top of those four bodies. This is the first big lesson hiding inside this thought experiment. Our intuitive sense of a lot of asteroids is wildly disconnected from actual physical mass. We imagine millions of objects and assume that must translate into a proportionally massive threat. But space is not painted with a uniform brush. A small number of large bodies utterly dominate the mass budget, while the overwhelming majority of individually named, tracked, and worried about asteroids are, in the grand scheme of planetary destruction, almost weightless. It's the same principle that shows up again and again across astronomy, from star formation to galaxy clusters. Distributions are almost never even. A handful of giants carry nearly all the weight, while a vast crowd of smaller objects make up nearly all the numbers. Now, let's actually walk through what a genuine every asteroid at once impact would physically look like, because the mechanics matter, and they are almost impossible to picture using everyday intuition. Ceres alone striking Earth would already be catastrophic beyond anything in human history. Ceres has roughly 130,000th the mass of Earth, small compared to our planet, but colossal compared to any asteroid that has ever struck us in recorded memory. The asteroid believed to have ended the age of the dinosaurs 66 million years ago, the Chicxulub impactor is estimated to have been somewhere around 10 to 15 kilometers across. Ceres is nearly 1,000 kilometers across. Its diameter alone is roughly 70 to 100 times larger than Chicxulub's, because impact energy scales dramatically with the size, and especially the mass, of the impacting body. An object like Ceres wouldn't just be a bigger version of the dinosaur-killing asteroid. It would be a fundamentally different category of event, releasing energy many orders of magnitude beyond anything the fossil record has ever preserved evidence of. An impact of that scale wouldn't just kill most life on the surface. It would melt substantial portions of Earth's crust, throw enough vaporized rock into orbit to potentially form a temporary ring or debris cloud around the planet, and plunge the entire globe into an impact winter so severe, and prolong that photosynthesis could shut down almost everywhere for years, if not longer. Now stack Vesta, Pallas, and Hygeia on top of that, and then every other fragment of the belt, all arriving in the same catastrophic instant. The heat alone, generated as these masses tear through the atmosphere and slam into the crust at speeds of many kilometers per second, would be enough to boil oceans across large portions of the globe. The kinetic energy converts almost entirely into heat, seismic shock, and ejected material on impact, and asteroid belt objects typically travel at relative velocities that can exceed 15 to 20 kilometers per second when their orbits intersect Earth's. At those speeds, even without factoring in the sheer scale of Ceres and its companions, the destructive potential dwarfs anything in the geological record. Simultaneous strikes across the globe, rather than a single localized impact, would mean there would be no safe side of the planet. Every hemisphere would be absorbing devastating blows within moments of each other. This isn't a regional catastrophe. It edges toward a planet sterilizing event, the kind of collision that some researchers argue could, in extreme enough cases, strip away portions of a planet's atmosphere entirely, a fate some scientists suspect may have befallen Mars in its own violent youth. But here's where we need to step back and ask why this scenario, dramatic as it is, doesn't actually represent a realistic threat, and understanding that is arguably more valuable than the shock value of the hypothetical itself. The asteroid belt exists precisely because these objects didn't collide into a single planet billions of years ago. Early in the solar system's history, the region between Mars and Jupiter should have coalesced into a proper planet, the same way material, clumped together to form Earth, Venus, and Mars. But Jupiter's immense gravity kept stirring the pot, speeding up asteroids, slamming them into each other, and preventing them from settling into a stable planetary body. Instead of becoming a fifth rocky world, the region became a graveyard of failed planetary building blocks, kept in a permanent state of near-perpetual orbital motion by the gravitational influence of the solar system's largest planet. That same gravitational shepherding is exactly what keeps the asteroid belt roughly where it is today, orbiting the Sun in a stable band, rather than raining down on the inner planets. There is no physical mechanism by which every asteroid could suddenly abandon its orbit and converge on Earth simultaneously. It would violate the basic conservation laws that govern orbital mechanics. Asteroids don't get bored of their current paths and decide to make a beeline for us. Their trajectories are locked in by gravity, momentum, and billions of years of dynamical history. This is why real planetary defense isn't structured around defending against apocalyptic mass convergence events. It's structured around statistics and probability, tracking individual objects one at a time, refining our understanding of their orbits year after year, and looking for the rare, specific case where a single body's path might genuinely intersect with Earth's at some future date. And this is where the story becomes less theoretical and much more current. In late December 2024, astronomers discovered an asteroid called 2024 YR4. and within weeks, it became the most closely watched object in the history of modern asteroid tracking. Early calculations suggested it had a startling escalating chance of striking Earth on December 22nd, 2032. By mid-February 2025, its estimated Earth impact probability had climbed as high as roughly 3%, the highest impact probability ever recorded for an object of its size, briefly triggering international alerts through the International Asteroid Warning Network. For a few tense days, an object between roughly 40 and 90 meters across, large enough to devastate a city if it struck a populated area, sat squarely in the world's collective attention. Then, as astronomers gathered more observations and tightened the uncertainty in its orbit, the odds of an Earth impact collapsed, first to under 2%, then rapidly toward zero, until by mid-2025, the probability of it striking Earth had fallen to a small fraction of a percent, effectively ruling out any threat to our planet for the foreseeable future. But the story didn't end there. Attention shifted instead to a strange secondary possibility. Could 2024 YR4 strike the Moon instead? Using observations from the James Webb Space Telescope, astronomers refined that estimate multiple times through 2025, watching the probability of a lunar impact rise from under 2% to nearly 4.5% by mid-2025, only for fresh Webb observations gathered in February 2026 to essentially rule that out as well, refining the asteroid's projected path enough to show it will likely pass the Moon at a safe distance of over 20,000 kilometers. The entire episode, from panic to reassurance to renewed uncertainty to final resolution, unfolded not because the asteroid's actual path kept changing, but because our knowledge of that path kept sharpening as new data came in. It is a vivid, real-world illustration of how asteroid risk actually behaves. Not sudden, dramatic swarms descending on Earth all at once, but single objects whose fates are gradually clarified through patient, methodical observation. This is genuinely how planetary defense operates today, and it's more sophisticated than most people realize. Facilities like NASA's Center for Near-Earth Object Studies continuously calculate and refine the orbits of tens of thousands of known near-Earth objects. New observatories are dramatically accelerating discovery rates. The Vera Rubin Observatory, which began science operations in 2025, has already demonstrated the ability to detect around 2,000 new asteroids in a single 10-hour observing run, and is expected to discover well over 100,000 new near-Earth objects over the course of its decade-long survey, alongside millions of additional asteroids throughout the solar system. NASA's dedicated NEO-Surveyor mission, a space telescope purpose-built to hunt for hazardous asteroids using infrared light, is expected to identify roughly 2/3 of all near-Earth asteroids larger than 140 meters within 5 years of full operation, climbing toward 90% coverage within a decade. In other words, humanity is rapidly moving from a species that occasionally stumbles across dangerous space rocks to one that maintains something closer to a comprehensive early warning system for the entire inner solar system. And crucially, we're no longer just watching. In September 2022, NASA's DART mission deliberately slammed a small spacecraft into an asteroid moonlet called Dimorphos, successfully altering its orbital period around its parent asteroid Didymos, proving for the first time in human history that we can physically nudge a hazardous object off a collision course through kinetic impact alone. It wasn't a movie. It was real, it worked, and it fundamentally changed the calculus of planetary defense from purely theoretical to demonstrably achievable. If a genuinely dangerous asteroid were ever identified years in advance, and years of advance warning is exactly what our growing detection network is built to provide, humanity now has a proven method for deflecting it. So where does that leave our original thought experiment? The every asteroid hits Earth at once scenario functions less as a realistic threat and more as a kind of cosmic thought exercise, a way of making scale viscerally comprehensible. It teaches us that the asteroid belt, despite containing millions of individual objects, is astonishingly diffuse and overwhelmingly dominated by just a handful of large bodies. It teaches us that even the combined mass of everything orbiting between Mars and Jupiter amounts to a small fraction of our own moon, itself dwarfed by Earth. It teaches us that true planetary catastrophe requires an object roughly the size of a dwarf planet, something on the scale of Ceres, not a swarm of city-sized rocks, however numerous they might be. And it teaches us, by contrast with 2024 YR4 and the steady, unglamorous grind of orbital tracking, that the real danger asteroids pose to Earth isn't apocalyptic convergence, but quiet, individual uncertainty. A single, unseen, or poorly measured object slipping through the gaps in our knowledge. Step back far enough, and the entire asteroid belt, all those millions of tumbling worlds that never were, occupies a region of space so enormous that even concentrating its full mass wouldn't come close to matching a single ordinary planet. Compare it to Earth, And the belt looks less like an army poised to strike and more like the scattered debris of a construction site the solar system never finished clearing away. A graveyard of planetary ambition interrupted by Jupiter's gravity 4.6 billion years ago. And yet, scattered and diffuse as it is, buried within that debris field is exactly the kind of raw material, water-rich, metal-rich, in some cases even carbon-rich, that future space missions may one day mine to build the infrastructure of a spacefaring civilization. The same objects that, in our thought experiment, represent apocalyptic potential also represent, in a very different context, resources and scientific treasure, frozen time capsules, from the earliest days of our solar system. So no, every asteroid will never hit Earth at once. The physics of orbital mechanics simply won't allow it. But sit with the number for a moment anyway. 3 to 4% of the mass of our moon, spread across millions of individual worlds, all of it a footnote next to the planet you're standing on right now. It's a strange kind of comfort and a strange kind of humility to realize that the sky above us, which can feel so vast and so threatening, actually holds remarkably little mass compared to the ground beneath our feet. The real question was never whether the asteroid belt could destroy us all at once. It's whether, among the millions of individual objects still quietly drifting through the dark, there's one small enough to go unnoticed and precise enough to matter, and whether we'll be watching closely enough, decades before it arrives, to make sure the answer stays no.